going to coffee, we can gather here and take a. Outside is also okay. We could decide after the seminar. So before taking too much time, I'm very happy to introduce Luca Santoni. He's going to talk about dynamical tidal response of Schwarzschild black holes.
Thank you, Borna. Thanks for the invitation, and hi, everyone. So, in fact, probably I should apologize that instead I will be talking about low numbers. And I will be discussing a work that we just finished with Oscar, who's also here. And in fact, I have to acknowledge that he has done the heavy lifts in the work. And also with Daniel Glazer, Austin Joyce, and Maria Rodriguez. And I would like, so of course, a lot of things have been said, so I will not repeat, but let me just stress once again a very simple thing that I think is obvious to everyone, that in the past few years, let's say, different methods going from scattering amplitude, double copy, EFT, black hole perturbation theory, densimetry, and so on, have revealed the striking simplicity of gravity, and in my opinion, yet to be fully understood. For instance, black holes, GR, famously are assembled with microscopic constituents, but behave like maximally chaotic systems with a rich entanglement structure. But still, the classical features of black holes are surprisingly simple, okay? But the message that I want to convey is that not only do black hole solutions are simple, but they are perturbations, okay? And some aspects of this simplicity are well understood in terms of hidden symmetries or general relativity. Others remain a bit mysterious, I have to say. One simple example in this, let's say, simple story of gravity is something that is very well known, which is the isospectrality, the fact that quasi-normal modes, you have 2 degrees of freedom, right? And these 2 degrees of freedom have characteristic frequencies if you perturb a black hole and you impose certain boundary conditions, as we have heard. And it so happens in general relativity that the frequencies are exactly the same for these 2 degrees of freedom, and this is something that has been known, and it's true for massless spin 0, 1, 2, and also partially massless fields, and has been known since the 70s from Chandrasekhar. Okay, I will go back to this at the very, very end. And another intriguing example is arises from the study of tidal deformability, and phrased, let's say, in the language of effective field theory. This means that black holes, they behave like elementary particles, okay? They are indistinguishable from elementary particles, at least as far as the static regime is concerned, as you have heard from, for instance, Lam's talk, and you will hear more from Alessandro after this one. And of course, we all know that tidal effects, they change the dynamics on the spiral. The message is that if you want to go, well, as we go, let's say, toward the area of precision physics with gravitational waves, we need accurate waveforms, okay? Which means that we have to understand the physics, the dynamics, conservative and dissipative dynamics of binary systems very well, okay? And this in particular includes subleading effects, okay? And so it's a very well defined and motivated question to ask what happens if we go beyond the linear and static regime for the tidal effects, okay? There are various reasons. For instance, subleading effects can be useful to put leading order results on firmer grounds. You can introduce some systematics if you neglect them. They can be useful to recalibrate effective models, improve waveform, and so on and so forth. And from the theoretical side, they can reveal some interesting pattern regarding the fundamental properties of gravity. And in particular, they're also especially relevant whenever leading order effects are 0, like for black holes. Okay, so this is just to say that it's very well motivated both theoretically and observationally. And there are 2 types, broadly speaking, of subleading effects. One is nonlinearities, which is what Filippo talked about. I will mention another type of subleading effect, which has to do with the dynamical response. Okay. These are the two possible directions, let's say, at least in an AFT sense. So I will focus on time-dependent tidal effects for black holes, and I will show how to compute a possible way of how to compute dynamical numbers. Okay, there are, of course, results already in this context, but most of them, at least in the gravitational sector, so far as I know, they are all incomplete. There are some examples in the scalar field, but so I will show you how to complete the calculation of dynamical numbers, not only regarding the universal part, but including also scheme-dependent finite terms. Okay, and I will comment on perhaps some interesting symmetry pattern at the end. Now, let me just start with, this is something that you have seen already from Filippo. So from a post-Newtonian or Newtonian intuition, let's say. So in Newtonian gravity, you just have this term, this one, and this one. And as Filippo has shown, in fact, if you go to the post-Newtonian regime, you start having RS over R powers, okay? And this is for the linear response, is the amplitude external tidal field, and K is the linear lab number. At subleading order, you can have different effects coming up. At quadratic order, as Filippo has shown, you have something that is quadratic in the amplitude, and then you can have, once again, this famous P2 that Filippo was showing, and then plus post-Newtonian corrections. I will focus on the second line, in which you can have time-dependent effects or frequency corrections, okay? Now, this is a very zeroth order zeroth order thing that I can write down, but there are some questions that emerge. For instance, are there non-analytic contributions in R? So far we have written only polynomials. Are there ambiguities in the definition of these coefficients? Okay. How do we describe dissipation? So all these questions need to be addressed if we want to discuss about both nonlinear effects, but this has already been discussed, but also time-dependent effects. And for static nonlinear response, it turns out that there are no non-analytic corrections in R, okay, which was mentioned before already, and probably Alessandro will have something to say about. And but non-analyticities and running appear at finite order in the frequency, okay? And more in general, one may worry about whether the definition of these lab numbers is a reparametrization invariant, or that maybe the split here is ambiguous, because if you imagine going enough powers in R here, maybe at some point there will be an overlap, okay? And in fact, ambiguities can arise in general relativity because it's gauge theory, and these ambiguities need to be addressed. And a conceptually clean, let's say, an ambiguous way of doing that is through effective field theory, okay? And of course, as we know, binary systems are challenging because there are different scales involved in the problem. And the EFT is a very powerful framework that allows us to disentangle physical effects that enter at these different scales. I will focus on, let's say, in this tower of effective field theories, I will focus in a simple regime in which, let's say that the object has radius capital R, and D is the orbital radius. I want to put myself in a regime in which we are far enough from the object, such that the object looks like a point particle in some sense. But of course, I want to neglect the binary dynamics for the moment, okay? So in the end, we will have a one-body FT, which is what already Filippo has mentioned. In this case, I want to go slightly beyond that because I want to include dissipation. So finite frequency effects are usually associated also with dissipation. In Filippo's case, the object was not rotating, so there was no dissipation. Everything was spherically symmetric. Here, we cannot avoid doing that. So how we do that? Well, the idea is very simple. So as we said, far enough from the object, we start from a point particle, and let's write the word line of the point particle, okay? Then we need to probe the point particle. So you have to tell me what is the dynamics in the bulk, so what are the fields that probe the point particle, and so I need to add some, let's say, Einstein-Hilbert action, because this is what I will be focusing on. And of course, there is an interaction. So I need an operator that describes the interaction between the external fields and the point particle. And I can write in this way, okay? E and B are the electric and magnetic components of the Weil tensor, okay? I will be focusing on gravity, so no scalar field and no spin one. This is just gravitational perturbations, okay? And QE, QB, you can think of them as carrying all the information about these interactions. So they can be composite operators depending in a very complicated way on the internal degrees of freedom and so on, okay? Think of the hydrogen atom. If you have an hydrogen atom and you send in some photon, this photon can be absorbed. So you can think of these additional degrees of freedom as being the energy levels of the hydrogen atom, okay? Now, this includes, as I said, a tidal response, a dissipation, absorption across the horizon, viscosity, and so on and so forth. And this is in terms of Feynman diagrams, if you want, this is a simple diagram that corresponds to this type of operator. Now, what we do is we want to integrate out these degrees of freedom. In other words, we will be solving for Q in linear response theory. Filippo went slightly beyond that, but for the moment, let's say linear response, but including finite frequency effects. More precisely, we need, since I want to account for dissipation, I want to use an in-path integral. So this is what I will be computing. And in the end, integrating out, so doing this path integral boils down to finding, to this type of interaction, okay? Where I have a quadratic operator in this E field, and there will be some two-point function of Q. In the end, of course, I don't have control over this two-point function of Q, but in the spirit of effective field theories, we'll parameterize this in the most general way, okay? So it doesn't matter in the end. In fact, I could have started directly here. So without going through this integration, I could just use my Schwinger-Keldysh rule and write down the most general action that is compatible with these rules, okay? For non-rotating objects, I want to take advantage of SO3. So the most general object that I can write down is just a product of Kronecker deltas. Of course, I didn't mention, so maybe I'm going too quick, but please stop me. So here, these 1 and 2 are the labels that tell me on which branch of the contour I am in this closed time path contour. So, and I was saying that the two-point function of Q is the product of Kronecker deltas times some function of time, okay? So this is the effective interaction. And now what we want to do is, we are in the EFT. I want to find the response if I perturb the system with an external tidal field. So I will be expanding the metric as Minkowski plus some tidal field plus some response, okay? This is I will be working in the Schwinger-Keldysh basis, in the Keldysh basis, okay? This is H plus and H minus. And now I can use this gamma in to compute the one-point function, okay, for the response. I'm just essentially, in terms of diagrams, this is the process that I'm interested in. So this is the external tidal field that interacts with the word line, okay? Then there will be some two-point function of Q, so something happens inside the object. And then I want to extract the response, okay? So I just want to compute a very simple process. And if you want, in the end, we'll just, so this is our effective interaction. So this is the one-point function. And we will expand this F in this way in powers of the frequency. This lambda 0 is the static lab number. This is the dissipative number, if you want. And this is the dynamical number that I want to compute. Okay, so in this sense, the EFT is a systematic, unambiguous, gauge invariant, and so on. So the definition of this coefficient is gauge invariant, and so on. And I want the way, so of course, now you have these free coefficients. Either you constrain them experimentally, which you can do, or you compute them. So you need you give me some UV model, I perform a matching, I compare the EFT. In other words, I compute some process here. I do a similar calculation in GR, and then I just compare. Eventually, in fact, in reality, it's better to, instead of comparing the metric, to compare something that is gauge invariant to avoid ambiguities, to make sure that everything is, so I'm computing the same quantity on both sides. So I will be computing, in fact, not the 1-point function of H, but the 1-point function of Weil, because it's gauge invariant around the flat space, okay? So I will just compute the Weil tensor in the EFT, the Weil tensor in GR, and I will just equate the two. No, here there is no orbital frequency. I'm just saying that the isolated object with an external tidal field which has a mild time dependence. I don't know. In the end, yes. Yeah. Yeah. Which scale? Sorry. Yeah. So I'm saying that whatever, so these x degrees of freedom are degrees of freedom on the word line. I'm assuming that their dynamics is much faster than the external dynamics. Yeah. Well, yeah, covariant. No, well, I know that, well, because if you do a gauge transformation, it will not pick up, it will transform as in the right way. A linear order, it doesn't transform. So you take x that goes, yeah, everything is linearized. Okay, so let me show you, first, let me start from the GR side. And for convenience, since eventually I will be working in DIMREG, I will do the calculation in generic dimension. And for simplicity, just for illustration, I will be focusing on the odd sector, or the vector sector, more precisely in the generic dimension. So this is my decomposition for the metric perturbation. Okay. Now we are no longer around Minkowski. Now we are around Schwarzschild. So it's Schwarzschild plus h mu nu. Okay. And I will fix a gauge, in particular the Regge-Wheeler gauge, and the equation for the degree of freedom is this one, and this is the Regge-Wheeler, let's say, generalization of the Regge-Wheeler potential in high dimensions, okay? And R star is the tortoise coordinate. Now, and I want to use, there are different ways of solving this equation. Of course, you cannot do it in analytically, but I will be using, let's say, something that has to do with mesh asymptotic expansion, more precisely boundary layer theory, if you want. So I will introduce three different zones, okay? A near zone, okay? An intermediate zone, which is valid, let's say, up to 1/omega, so it's pretty large, and a far zone. And then we solve the equation separately, and we match the boundaries, okay? Now, in fact, we will not need the far zone. I will comment on that. But yeah, if you want to solve everywhere, that's the logic. And let me go back for a second in 4 dimensions. Okay, this is the equation in 4 dimensions. In the near zone, everything is very simple. It's just the usual wave equation. So these are the 2 solutions. You impose a in boundary condition, and this is the near zone solution for this psi field. Okay. Now, B is an amplitude which eventually is related to the amplitude of the external tidal field, so I keep it generic. And then how about the intermediate zone? Well, in the intermediate zone, the omega squared term that, let me see if I can show you. So in the near zone, these terms blows up, right? If you are far enough from the near zone, this is genuinely a small term, so I want to treat it perturbatively, okay? And I can expand in this perturbative sense. I can expand the field in powers of the frequency, okay? And order by order in the frequency, I will fix the integration constant by matching with the near zone. This, in other words, I will take the small frequency limit of the near zone solution and equate it to the near zone limit of the intermediate zone solution, okay? And eventually, for instance, let me just give an example. If you are if you take the solution for the intermediate zone and you expand it at large distances, this is what you find, okay? And this should be contrasted with the post-Newtonian intuition that I wrote at the beginning. So you have the tidal field, you have some frequency correction to the tidal field at linear order, you have some 1/r cube, so that something that resembles some frequency-dependent lab number, let's say. And then you have higher powers of R and so on and so forth. But then you start seeing already some differences. For instance, there is this log, okay, that we didn't write in the beginning. In fact, there is some logarithmic scaling in R in front of this omega squared term, okay? Something that scales logarithmically in R. And in fact, this has an interpretation in terms of RG running in the EFT, as I will show you. By construction, there are no non-analyticities in frequency, okay, in the intermediate zone. If you were to expand this in the far zone, then the story is slightly different, but here everything is perfectly fine, okay? Now you can even go to the far zone and you can ask yourself, well, let me define a far zone that goes from omega r order 1 up to infinity now. Once again, I repeat my logic. So I compute the solution. I match across the boundary between intermediate and far zone, okay? I turn the crank and so on and so forth, and I can compute some observable, for instance. And if you do so, for instance, you can compute scattering amplitude, and this has been done this exercise has been done I mean, the matching with the EFT has been done for a scalar field in these works, okay? What we show is that this far zone constructed in this way reproduces the MST result, at least in a scalar field example. But as I said, that's all I have to say about far zone. From now on, I will forget about it, okay? Because it's not needed in the EFT. The EFT is valid already in the intermediate zone, so I don't want to go I don't want to compute a scattering amplitude. For me, it's just enough to compute correlation functions in the intermediate zone, okay, and perform the matching there, okay? Okay, let's go back to the EFT. Now we have, let's say, this solution. This solution is the intermediate zone solution, which carries, some UV calculation in perturbation theory in the frequency, and we want to match to the EFT, okay? And let me stress once again that the EFT is valid in the intermediate zone, okay? How do we do that? Well, as I said, let's compute the 1-point function of the Weil tensor. Since previously I was showing you the Regge-Wheeler equation, here I need to compute the 1-point function of the magnetic component of the Weil tensor, this B, okay? So after some algebra, let's say, so you just have to compute, as I said, this process, which in the end is not too bad. So you have an external field, you have this 2-point function of Q, which in the end is parameterized by this function f, okay, which let me Fourier transform, it becomes a function of omega. And then you have some external propagator, okay? That's the process that's done computing. After some algebra, what you find is something like so, okay? So there is the tidal field plus some response, and with some time-dependent coefficient. And let me remind you that the expansion in powers of omega of this f are precisely the static and dynamical numbers and the dissipative numbers. Here, once again, I'm in d dimensions. Epsilon is 2 minus d over 2, and mu is an arbitrary scale. So here I introduce a scale mu, let's say, in such a way that these lab numbers, the dimensions of these lab numbers don't change when I do dim reg, okay? Is the usual story. Now, of course, this result is valid exactly in flat space, but following the logic of a work that this work here, which, well, in some sense, is what I'm showing you is a slightly modification, but it's already contained there, the logic. You want to reconstruct gravitational nonlinearities, okay? You want to include the gravitational effects. And a way to do it, once again, you can do it perturbatively. For instance, you take once again the regular equation d dimensions, all that depends on G Newton or RS, you put it on the right-hand side, okay? And you once again, you turn the crank and you start solving this equation order by order. Very quickly, how do you do that? First, you solve the homogeneous equation, okay? Not very surprisingly, these are the two independent solutions. And by the way, if you now compare with what I was showing you before, these coefficients are not completely arbitrary. They are just related to f. So I just take the solution, I compare with the previous Weil tensor from this solution, and f is related to this to the ratio of these coefficients. Well, in some sense, we already solved the flat space, so these coefficients are not independent. Yeah, it's a more complicated way of saying the same thing, but yeah. But then you need, so once you have the homogeneous solution, you want to compute the particular one, okay? And which can be done using a Born series, for instance, okay? And in the end, everything boils down to computing loop diagrams like so. You are just reconstructing, if you want, your nonlinear background, okay? Adding powers of over S and omega. So in the end, after you do so, you find a solution like this, up to quadratic order in the frequency. Okay, so this is EFT, where now you have this log of mu r, and this logarithmic running precisely comes from this type of diagrams, if you want. And of course, there are also other terms here. There are this 1 over epsilon. So as we mentioned, as I mentioned before, there is some divergence that that's why we introduced dim reg in the first place. Okay, so we need to regularize this object. So you need to introduce some counter term in your theory, but that's a standard procedure. So I'm not saying anything new. Here, you mean? I think it should be, yeah, there are some dimensions that you have to be careful about. There is 1 over 50 here. I think it should work, right? Because this one compared to this one, the dimension should be fine. Yeah, it's the only, once you say that your order omega squared, the only thing that you can introduce is G Newton. So, of course, when you do this calculation, you have to make sure that you go up to G7, because if you stop before, the result is not consistent. Yeah. Yeah, there are a couple of differences. So first, they just focus, well, there's already some interesting progress. So they focus on a scalar field, and they do the matching, comparing far zone observables, let's say, for instance, scattering amplitude. While here I'm just saying, well, there is no need to go to the far zone. Let me just do the matching instead of scattering amplitudes. I'll do the matching with the correlation functions. But yeah, it's a matter of taste, but yeah. And so we subtract the infinities in the standard way. So we introduced some new coefficients, let's say renormalized coefficients, and then you plug them back, and you find that the renormalized solution for this Regge-Wheeler field looks like so. Okay, and then we need to do the matching. So we take this guy and we compare with the intermediate zone solution that I was showing you before, if you remember. If you do the matching, well, doing the matching essentially boils down to fixing these coefficients that so far are arbitrary. Okay, and these coefficients now are fixed to be the following. Okay, and you see that now these are constant coefficients. There is some log mu r as expected. There is some linear piece in the frequency, quadratic piece in the frequency, some big numbers, but of course these are scheme dependent. Okay, so I don't, yeah, and also, yeah, these two. And what we do is that now we take the ratio, because f of omega was defined as the ratio between these coefficients, and this is what we find. Okay. This was done for the odd sector, but similarly, you can do exactly the same procedure for the parity even sector, okay, for the other degree of freedom. So of course, there are some technical details, but let me just focus on the main points. Let me just highlight the main points. First of all, I want to stress that in all the examples that we find, there is a relation between the coefficient of the log and the imaginary part. You see from here that the coefficient of this I omega raised to the 6 is precisely -1, the coefficient minus the coefficient of the log. And this is true in all the examples that we have been able to check. So such a relation holds, okay? And yeah, this is the first observation. Second observation is that the imaginary part, these guys, and the coefficient of the log in both the even and odd sector, they are exactly the same, okay? There is some sort of duality between even and odd, and but this was kind of expected, like it's a natural consequence of, so a different realization, if you want, of the isospectrality that I was mentioning in the beginning. Now, the question is, why only these coefficients and not these other numbers? Why are not the same? Well, the answer is pretty simple, because we used a regularization scheme that breaks the symmetry explicitly. So the Chandrasekhar duality is broken in higher dimension, okay? Of course, you can always choose mu in the two sectors to be, so you choose different scales in the two sectors, and you fix ad hoc your scheme in such a way that they are the same, but the symmetry is broken. So there is no reason why finite terms should satisfy the duality. But at least the universal pieces, so the imaginary parts and the log, they do, and this is a non-trivial cross-check of that what we are doing is fine. So let me just conclude saying that the summary is very simple. What we did was to compute the gravitational dynamical numbers of Schwarzschild black holes, and as it was known, I would say, as opposed to static response coefficients, the dynamical numbers have some RG running, okay, in line with the standard EFT expectations. But of course, the coefficient of the log, as I said, was known before. What we did was to compute the finite scheme-dependent terms, okay, for gravitational interactions. As I said, it's worth mentioning once again these two works, and also there are other two talks at this workshop that I believe, well, they nicely connect to what I'm presenting. So, but let me go back to some questions, in the sense that I believe that this simple story of gravity is not at the end, in the sense that it would be nice, for instance, as a very simple question, to see if a different regularization scheme, so to check this duality using a different regularization scheme that preserves the symmetry explicitly, for instance. Now, an interesting question is, at least to me, which at the moment I don't have an explanation for, how general, fundamental is this relation? Is it related to fluctuation, dissipation? Is it something different? Let me stress that just to mention why I find this interesting is because the imaginary part, this guy, in fact, turns out to be fixed by symmetries. So ladder symmetries tell us that this factor, so in other words, yeah, they are related to ladder symmetries. Lam mentioned this a little bit. So it seems that this suggests that maybe there is some hidden structure also at quadratic order in the frequency, maybe not for all the terms, but at least for the universal ones. And I have to mention that is this similar, you can ask the question, is this an accident at order omega squared, or does it survive at subleading order in omega? And the answer is that it seems that at least in the examples that we checked, there is an interesting pattern also at subleading orders in the frequency. So this is very suggestive that there is still perhaps a further structure to be mined in black hole response coefficients. Okay, I will stop here.
For questions? Yeah, thanks for interesting talk. So for this imaginary part, omega FL, can you say it's some structure from the later symmetry, but what's this quantity correspond to in the symmetry case?
This quantity is what? Say it again.
What does this quantity mean in this later symmetry?
Well, it's related to the conserved charge of one of the generators of this ladder symmetry. So I don't think I have a physical intuition to give, but yeah, at least it's proportional to that. I don't think we ever got to the bottom of this fact that I'm mentioning, but at least that it seemed, to me, it is a suggestive that there is some non-trivial structure maybe to be understood.
Thanks for the very nice talk. Just to connect to Davide's talk to make sure I understand. So he also computed finite corrections, but maybe his scheme is different with the shell and everything. So do they agree or probably not? Or
very good. So what Davide was doing was for a scalar field. So it's not yet possible to compare. But in fact, yeah, we were discussing before, and for sure, when they do it for gravity, then it would be nice to compare, and also to see if one can define this use a different scheme, and maybe that manifestly preserves the symmetry and so forth. So this, yeah, they will tell us, I guess.
4 more questions. No.
Thanks, Luca. Very, very nice and inspiring. So you were mentioned that regularization breaks Chandrasekhar duality, dimensional regularization breaks Chandrasekhar duality. Do you think there is another scheme where it's preserved, or do you think it will be broken in the scheme?
I guess there is. Well, I guess it's possible. I don't have, but I don't have an example. You mean a different, not using the MREG? Yeah, I guess so. Why not? But I don't have an example. So, but let's say that I don't have anything. I cannot say no, so I would say yes.
And do you think it's a feature of linear perturbations, or do you think it
this one?
No, the fact that magnetic and electric.
I think it's beyond that. So in fact, that's a question that I've been thinking about, but I never tried to really understand it. Yeah, this is another thing that I never got to the bottom of. So I think that there is, but yeah.
So if there are no other questions, we can thank this.
Thank you.